Welcome to the PanCap video, Database Consolidation with TiDB. My name's Jeff and I'll be your guide for this journey. So during this video we will discuss the purpose of database consolidation, resource isolation and control in TiDB, storage tiering and differentiated high availability in TiDB, and last but not least we'll cover some customer use cases. So let's begin with why. You're probably asking yourself, what is the purpose of database consolidation? Or in other words, why would anyone desire to consolidate databases? In the world of databases, data consolidation refers to the process of combining multiple sets of data from different sources or databases into a single location. This can be achieved through various means such as data warehousing, data integration, or data federation. So data consolidation requires new data models and ETL code. On the other hand, database consolidation refers to the process of combining multiple databases into a single database or cluster. The databases are moved as is to the new environment. So for example, you go from 10 separate database instances to a single database instance. There's no need for data model changes or ETL. Database consolidation is typically done to simplify database management, reduce cost, and improve scalability. While the terms data consolidation and database consolidation are related and may involve similar technologies and techniques, they're not interchangeable. Data consolidation focuses on bringing together different sources of data, while database consolidation focuses on reducing the number of databases in use. In summary, data consolidation is about consolidating data from different sources, while database consolidation is about consolidating multiple databases into one. So why do we need to do data consolidation? One is to prevent over-provisioning. So in a traditional one application per database environment, we always adopt the method of purchasing excess hardware resources to cope with future business growth and load fluctuations in order to secure system performance and reliability. For example, a critical system may initially only require 100,000 queries per second processing capacity and 100 terabytes of storage space. But in our architectural design, we often need to reserve more than twice the required computing power and storage space. Next, we have development and operations inefficiency. This one's pretty simple. There are two aspects here. One, it takes more DBAs to manage 300 databases than it does to manage one. I pulled the number 300 out of thin air. There's nothing magical about it. I'm just using it as an example. Two, 300 database installs requires more resources to one than one single database install or one single database instance. Finally, we have limited capacity to scale. So scaling a single database cluster is much easier than tracking and scaling 300 of them. Once again, 300 is a made-up number. So here's some reasons why you may need to scale your environment. So the first one are sudden surges in traffic, load, and data due to unexpected events. These types of events often result in an urgent need to scale. The key word is urgent. This is much easier to anticipate in a consolidated database environment. Next, we have excessive accumulation of historical data seriously affecting online operations. So this is the inability to separate cold and hot data. Next, we have failure to meet the needs of both transactional and analytical workloads. That's a big one. And finally, difficulty in controlling costs due to the inability to recover and reuse resources after business units enter a decline phase. This is much more difficult to do when you have multiple, in our case, 300 databases than when you have one. I'll let you in on a little secret. Not all databases do a great job at database consolidation. Shocking, I know. But before we start, I need to warn you about something. I'm going to use the term multi-tenant. Unfortunately, this term means about 1,000 different things in the database and cloud world. We're going to keep it simple. When you hear multi-tenant, think about it in terms of database consolidation. Our definition of multi-tenant will be a multi-tenant database is one upon which we can implement database consolidation. That is, a single database cluster that will effectively manage multiple corporate databases. You can think applications here. So let's say you agree with me and you decide you need to consolidate your databases. What capabilities should you look for in your new database? Well, the first is isolation. Each database may have different performance characteristics, data volumes, and availability requirements. Our new database must be able to manage these divergent requirements. This is not a problem for your single tenant databases because, well, they only run a single application. You can customize the instance to your heart's content. On the other hand, your new multi-tenant database must have the ability to customize the setup on a per application basis. Another way to say this is a per database basis. For example, some applications have a higher priority and often require more computing and storage resources, while other applications are idle for long periods of time. So likewise, some systems experience sudden increases in workload after certain periods of use, while other applications enter a period of decline, going from being very busy to having a low workload. Our new database must be capable of resource control, which means it can allocate CPU processing power and I/O accessing capabilities to applications based on their needs, thus dynamically adjusting the allocation of computing and storage resources among the various applications. We also need the capability to separate historical and current data, as well as different demands for data replication. This is high availability. From various applications, we will explain these features in detail later. Next up is scalability. In order to avoid over-provisioning costs, our database must support easy horizontal scaling. This means that when migrating from a single tenant to a multi-tenant database, we do not have to reserve processing power and storage space. Instead, we can wait until the data volume and load reaches a predetermined point and easily expand our computing and storage capabilities. Likewise, when the load decreases, we can easily reclaim our computing and storage resources without affecting the user experience or the application. Next, we have translytical capability. Okay, Forrester Research made up a word. I think we need to describe it. So translytical describes a new generation of data platforms that combine transactional and analytical processing capabilities within a single system. Traditional single and multi-tenant databases often cannot handle both transactional and analytical business use cases at the same time. They require time-consuming ETL conversions to be implemented in two different database systems. For example, you run your transactional workload in DB2 and your analytics workload in Teradata. So this approach requires multiple systems, DB2, Teradata, could be others as well, and an ETL process to move the data from the transactional system to the analytics system. This is a lot of work and usually winds up being a maintenance nightmare. Next up is easy to operate. This one should be reasonably self-explanatory, but let's take a look at it because it's important. Due to the large number of single-tenant systems migrating to multi-tenant databases, continuous performance and high availability monitoring have become an essential feature. And by essential, we mean required. You have to have this. A convenient and quick resource scheduling interface can help us simplify operations and improve response times, thus reducing operation and maintenance costs and improving efficiency. In other words, easy to operate. And finally, lower cost and high efficiency. Being able to dynamically allocate compute power and storage resources according to the workload demands of an application, separating the scheduling of computing and storage resources, this all allows us to achieve more precise cost control after data consolidation. Now that we've described a bunch of this stuff, let's talk about resource allocation and control in TiDB. One of the biggest challenges we face when planning to consolidate single-tenant databases into multi-tenant databases is how to ensure that the user experience of the various systems meets or exceeds expectations. It's important to remember that users will compare the old single-tenant environment to the new multi-tenant environment. They will be very disappointed if they notice a drop in performance. We know that disappointed users will complain about this nonstop. They won't care that the new system is more efficient and reduces cost. The diagram on the left shows a traditional single-tenant environment Recall, this architecture makes optimizing the database easy because you tune the database for the one application running on it. On the right, we see a multi-tenant environment. Notice the box around the databases. This signifies that our individual database instances are consolidated and running in a multi-tenant environment. So in a multi-tenant environment, we must be able to tune computing power and storage for the many databases running in the box on the diagram. Traditional multi-tenant databases often view their computing power and storage as a large resource pool, or parent resource pool, which contains all CPU, memory, and I/O resources. Before consolidating data, we must create a corresponding sub-resource pool for each existing single-tenant system. For example, in the picture, the parent pool consists of 64 CPUs, 1,000 gigabytes of RAM, and 10 terabytes of storage space. Assume we must accommodate 3 databases, or tenants. We will call them DB1, DB2, and DB3. We will place each of these in a dedicated resource pool that we create. Let's begin with DB1. We will create resource pool 1 and assign DB1 to it. This is a lightly used database, so we will only assign it 8 CPUs, 32 gigabytes of RAM, and 500 gigabytes of disk space. And we will limit it to 128 IOPS. Let's move on to DB2. DB2 needs a little more power than DB1. So we create a resource pool, call it resource pool 2, and assign it 16 CPUs, 128 gigabytes of RAM, and 500 gigabytes of disk space. We will limit it to 1,000 IOPS. Finally, we have DB3. DB3 needs far more capacity than the other two. We create resource pool 3 and assign it 32 CPUs, 512 gigabytes of RAM, and 5 terabytes of disk space. And we also will limit it to 10,000 IOPS. Our excess capacity over here to the right is 8 CPUs, 328 gigabytes of RAM, and 4 terabytes of disk space. Our new multi-tenant database has isolated the 3 databases from one another. This means that once a database reaches its limit, it cannot obtain resources from the others. That's important. This will be great in the beginning, but over the course of time, 2 problems may appear. Problem 1. Each system is restricted to a fixed resource pool, and when the system load changes, its resources are still limited to its own resource pool, resulting in the inability to quickly expand resources and possibly resource waste. For example, in the above scenario, if our DB2 suddenly experiences a heavy workload during an activity, I hope to allocate more CPU and IOPS to it so that it can smoothly handle the peak load. Unfortunately, DB2 can only use the CPU and storage resources in its own resource pool, which is in this case resource pool 1. This causes me to be unable to supplement computing power and storage capacity for tenants according to their needs. Another example. Assume DB3 no longer requires the computing power and storage capacity in resource pool 3. The CPU and I/O capabilities in the sub-resource pool can be freed up for use by other tenants, such as temporarily helping DB2 handle peak traffic. Due to the inflexible resource pool settings, we're still unable to meet this simple resource scheduling requirement. Problem 2. In order for the database to accommodate new tenants or temporary peak loads of certain systems mentioned earlier, we must reserve a portion of the idle CPU and I/O processing capacity in the parent resource pool. When a new tenant joins, we can allocate a sub-resource pool for them to ensure their operation. However, it should be noted that many new systems are not immediately put into production when they do go online, or they do require fewer resources in the beginning. If we can allocate idle resources from other systems to it, or simply not allocate resources to it, could we save computing power and storage capacity? Next, we will look at TiDB resource control. When we consolidate multiple single-tenant databases into a single TiDB cluster, we don't need to plan how big each tenant's resource pool should be. Instead, we will use resource groups to manage how much CPU, RAM, disk, and IOPS a user can access. A TiDB resource group is a logical concept that can be thought of as a set of database users, sessions, and SQL statements, which we refer to as database users. So in other words, we refer to all these as database users. An important feature of resource groups is resource quotas, which represent the investment in CPU time, I/O bandwidth, and IOPS and other indicators per unit database time. Each database user, and that is database user, session, SQL statement, can only use database resources within the quota assigned to the resource group it is bound to. With resource groups, we can control resources from the perspective of database users. For example, in the figure, the tenant DB1 database has just gone online and is in the test phase, so it doesn't require many resources. Therefore, we can bind DB1's users to resource group 1, which has low resource quota. Database 2 is online and under moderate load. The TiDB administrators bind database 2's user to resource group 2. Notice that resource group 2 is assigned medium quota. And you'll recall that DB3 is very busy. So the DBAs bind its users to resource group 3. This resource group is assigned maximum quota. Resource group 3's users have greater priority in resource usage even in the event of contention. So in summary, this resource management method based on resource groups achieves resource isolation from the perspective of database users, and it targets actual users, sessions, and SQL statements. This adds up to something very nice. We don't have to worry about how much each tenant's resource pool is allocated before we consolidate the databases. Next, let's consider change. I guess I need to be more specific. I mean changes in the way that our tenants are being used. Take the DB2 database, for example. Let's assume DB2 has experienced a significant increase in priority over time with an increase in load and concurrent access. In other words, it's a lot busier than it used to be. On the other hand, DB3 is now entering a period of reduced load and reduced concurrency. It no longer needs the resources allocated to it. Then, just to make this interesting, we migrate a new environment to our TiDB cluster, DB4. This tenant is not currently in use. If we manage resources through resource pools, we will need to reallocate resources for DB2 and DB3. This could result in downtime. Allocating resources for DB4, despite it being unused, would also be a waste. With resource groups, we can bind the users of DB2 to the resource group 3, which has a higher priority in resource allocation and a larger resource quota. For DB3 users, we can bind them to resource group 2 with the medium resource quota, so that the tenant's database does not need any adjustments. As for DB4, nobody uses it, so we don't need to consider its resource allocation at all. In this way, we allocate more for those who need it and less for those who need less. Now let's look at a scenario where the load on our cluster suddenly changes. In the beginning, database D2 has 2 users and a single resource group, 2. This resource group is assigned a medium resource quota. We know this because the priority equal option is set to medium. Imagine you get a Slack message warning us that a new product is launching tomorrow. This product will use DB2. While we appreciate the warning, it would have been very nice to have more than a day notice. So this application, denoted by user 3, will require several times more database resources than usual to handle the increase in load. Other services continue to run as usual. If we use a resource pool to increase the CPU and I/O capability of DB2, the services that previously did not require resource expansion will gain access to the newly added resources. Using a resource group, we only need to bind the relevant database users to the new resource group with larger resource quotas. Other users remain bound to the previous resource groups. In this way, we've expanded resources for those services that temporarily require more resource allocations. As shown in the diagram, we bind user 3 to resource group 3 with higher resource allocation quota. Let's return to our original diagram. Well, almost our original diagram. There's a slight but important difference. What happens if user 2 suddenly experiences a heavier load? Increases in database loads can occur due to events such as traffic switching or failover. So user 2 is bound to a resource group that is designed to accommodate normal database use. Fortunately, we can add a burstable option to this resource group. If burstable is enabled, the resource allocation quota of a resource group can be exceeded. This allows TiDB's free resources to be assigned to users who are experiencing atypically high use. Well, let's bring user 3 back into the picture. Recall that user 3 is a consistently heavy resource user, and user 2 is a sporadically heavy resource user. Using separate resource groups, including one with burstable set, provides us with a clever way of handling these types of situations. We have been focused on users, but remember, we can bind an SQL query to a resource group too. So take a look at the left-hand side of the diagram. We have lightweight query 1 that runs on DB1. It's an easy query that isn't resource intensive. We've assigned it to resource group 4. Notice the priority is set to low. Scanning to the right, we have resource intensive query 1 assigned to resource group 5. The priority is set to medium, and this query runs against DB2. Finally, we have resource intensive query 2, which has fire, which means it's really resource intensive. This query is bound to resource group 6. This resource group is the beefiest. The priority is high and burstable is set, which means that it can continue to exceed that for short periods of time. Next, we will discuss storage tiering and differentiated high availability in TiDB. Our previous discussion revolved around resource control. Next, we will look at features we can use to implement high availability in our TiDB clusters. The first one we'll look at is data replication. On the left-hand side of the diagram, it shows traditional single-tenant databases. Remember, there are many definitions of single and multi-tenant. In the TiDB world, a tenant is an application. A single-tenant database is used for a single application, and a multi-tenant database such as TiDB can effectively run many applications. So we're thinking of this in the data consolidation world. So in our diagram, DB1 is a single database that does not implement any data replication. There's one replica, and that's not even really true. There are no replicas. There's one copy of the data. DB2, on the other hand, has a primary database and a single standby database. There are two copies of the data. One is in the primary, and the second is a replica. DB3 has a primary database and two standby instances. There are three copies of the data. So, primary copy of the data and two replicas. So, adding replicas in this environment is difficult. It means you'd have to create new database instances and do a lot of stuff on the back end to connect them. Now let's look to the right-hand side of the diagram. This is what our three databases would look like if we did a complete database consolidation project to move DB1, DB2, and DB3 to the multi-tenant TiDB cluster. TiDB implements data replication by default. Notice that there are three servers and each one stores replicas of the data. This means if servers go down, we don't lose data. So when we're doing database consolidation, if the multi-tenant database can't customize the number of replicas for data in each tenant, the situation shown in the diagram will occur. That means we must meet the requirements of the tenant with the highest demand for high availability. In our example, that's database 3 or DB3 with its requirement for 3 copies of the data. To achieve this, we must reserve 3 independent multi-tenant database servers to meet the high availability requirements of the DB3 tenant with the highest demand. Keep in mind, DB1 and DB2 do not require such a high level of availability. It's recommended that they have 2 replicas, right? Just like DB3, that is 3 copies of the data. Hey, more is always better, right? Well, this is not what we want. We need a way to deal with this. Notice the change on the right side of the diagram. This matches the original environment. From a cost control and operational workload perspective, allocating a database 2 replicas, which is actually 3 copies of the data, seems somewhat wasteful. Of course, some multi-tenant databases may not need as many replicas for DB1 and DB2 as they have for DB3. The problem with this approach is that the multi-tenant servers prepared solely for DB3's high availability may also end up being idle and wasteful. We need a way to accommodate all levels of availability. In TiDB, compute and storage are separate. The storage layer is TiKV. It stores data as key value pairs. The storage layer is responsible only for storing and accessing data. TiDB server is the compute layer. It handles SQL processing, but it can push some filtering down to the TiKV layer. This helps with performance. You can scale storage and compute separately in a TiDB cluster. So let's take a look at our diagram. Look at Table 1 and Table 3. These two tables have typical high availability requirements. Notice that they have 3 replicas. Here's Table 1. Here's Table 3. Let's compare these two tables to Table 2. Table 2 is critical to our business and has a more strenuous high availability requirements. In fact, we've determined that we need 5 replicas for Table 2. So the question is, how do we configure this? Well, we will use TiDB placement rules to do this. First, we create a placement policy. Placement policy is another way of saying placement rule. We will name our placement policy P2, and we will use the followers option to set the number of replicas. In this case, we set the number of followers to 4, which gives us 5 copies of the data, or 5 replicas. Next, we issue a create table statement for Table 2. We include the placement policy option. Notice that we set this to P2. This means that Table 2 will have 5 copies of the data. Now we can customize the high availability level separately for each table and each partition. Compared with being only able to customize the high availability level for different tenants, this fine-grained control can save us a lot of resources. Next up is storage tiering. Storage tiering is accomplished using the concept of hot and cold data. Hot data refers to current data, such as product orders from the last month and user payments records from the last week. That is, data that we need to frequently query. Ideally, this data would be stored on high-performance disks such as SSDs. In contrast, cold data refers to historical data generated during past years of application operation, such as transaction records from the last 10 years, which may be rarely or even never queried again. It would be best to store this data on less expensive HDDs. This helps us save money on our database environment. In the design of a single-tenant database, some applications may have more cold data than hot data. If storing them in one database affects the efficiency of the database, it is necessary to separate them by hot and cold data, such as in database D1 shown in the diagram. By storing the hot and cold data separately in different databases, we save money and make it more efficient, but this type of arrangement would be difficult to manage. There are also some single-tenant databases that use designs such as partition tables, which store hot and cold data in different tables or different partitions within the same table. Periodic processing is performed on the cold data, such as deletion, backup, or migration, such as in the case of DB2 shown in the figure. The database DB3 represents that when designing for a single tenant user, there was no consideration given to how to separate hot and cold data, or the system has not been running long enough to generate a significant amount of cold data. So the cold data has not yet affected the system's performance. When you migrate single-tenant databases to multi-tenant databases without a solution for separating hot and cold data, there will clearly be a waste of hardware resources. For example, the hot and cold data in DB1 will use the same hardware resources, resulting in an unnecessary cost. When the cold data of DB1 and DB2 are migrated to the multi-tenant database, they occupy high-performance SSD storage. Also, the original partition design of DB2 requires additional attention and manual operation. This increases the DBA and system administrator's cost. After running for a while, DB3 will have too much cold data and will adversely affect its performance. So fortunately, there's a better way. Fortunately, TiDB allows you to deliberately place data into hot and cold areas using placement rules. So TiKV1, 2, and 3 are high-performance storage servers equipped with SSDs. These drives are much more expensive than HDDs. We want to use them to store hot data. In contrast, TiKV4, 5, and 6 are machines with high-capacity HDDs. These disks are slower than SDDs or SSDs, but have very low cost. We want to use them for storing cold data. As before, we will use SQL statements to create our placement rules. So take a look at the create placement statement in the middle of the diagram. This is very similar to the one we saw previously. We will create a placement policy named pcold. We will set two parameters, primary_region and regions. This will determine where TiDB stores the data for the tables that pcold placement rule uses. The constraints equal option specifies the disk type, in this case HDD. So when creating tables 3 and 4, we specify their placement policy as pcold. As a result, these tables are placed in an inexpensive storage servers TiKV4, 5, and 6, which, as we mentioned earlier, are designated for storing cold data. The high-performance SSD storage servers TKV1, 2, and 3 were designated for hot tables, table 1, and table 2 to use. It's important to note that we can partition some historical data, that is cold data, and set it in a separate placement policy. We can also modify the placement policy for a previously hot table or partition so that we can place it on storage servers where cold data lives. We can see that the placement rules in SQL provide fine-grained control for the storage location and high availability of each table in the multi-tenant TiDB environment. This helps us control data objects in the database consolidation process. So far, we've discussed isolation. What we haven't covered is how we want our multi-tenant database to respond to changes in load. Specifically, the changes in the load, really resource demands, of the individual applications. At PingCap, we call this differential scalability requirements. Before we begin, let's define unified storage and compute. It's right there in the title of the slide. It's pretty simple. Unified storage and compute means that compute and storage lives on a single machine. They aren't separated in modern databases like TiDB. In the diagram, tenant D1 has reduced its data volume via data optimization. Its concurrency has not changed, and the load from SQL statements remains the same. The DB2 tenant's data volumes remain unchanged, but there's been an increase in concurrency. This has resulted in a significant rise in queries per second. The DB3 tenant's SQL load and queries per second have not changed, but the data volume has doubled. The load on our three tenants have changed in different ways. Their demand for computing resources has changed too. If you were using a traditional database where compute and storage are coupled, this would pose a problem. You would be forced to implement a sharding strategy where each server provides computing and storage capacity. However, this will lead to difficulties in controlling costs because you can't really fine-tune control changes to each tenant. This also increases the complexity, which will increase DBA costs. An example will help here. Let's assume that in our compute and storage integrated system, DB1, the amount of data has decreased to 1/3 of its original size. If the server is removed because the data has decreased, it will lead to a reduction in computing power and a decrease in the number of CPUs allotted to other tenants. Similarly, although the data volume on DB2 tenant has not changed, the SQL load is increased and causing an increase in QPS and requiring more CPU computing power. In this situation, we must increase the number of servers. This will fix the data volume issue, but will add unneeded compute capacity to the environment, making it more expensive and potentially harder to manage. Finally, we have the DB3 tenant. The amount of data is doubled, and it is obvious that it requires double the number of servers. Once again, we have the problem of excess compute capacity. I think it's safe to say that unified storage and compute leads to situations where you have unused resources, because if you need compute, you must add storage, and if you need storage, you must add compute. This architecture is inflexible, it's difficult to control, and it's costly. We've seen the problems with scaling environments where compute and storage are coupled. Now let's take a look at TiDB and see how separating compute from storage makes our lives easier. So TiDB separates compute from storage. Compute is handled by TiDB server. Recall that this is the component that applications connect to. It handles SQL processing. Storage is handled by TiKV, and TiKV is a key value store. If we are constrained on the compute side, we add TiDB servers. If we are constrained on the storage side, we add TiKV nodes. The opposite is true too. If we have excess compute capacity, we can remove TiDB server nodes. If we have excess storage capacity, we can remove TiKV nodes. Once again, let's talk about the load variability among our three tenants that we discussed previously. So recall our previous discussion about DB1. Its data volume is decreased to 1/3 its original size. I know what you're thinking. Applications never decrease their storage volumes. Bear with me here. The SQL workload remains unchanged. So using TiDB, we only need to remove TiKV nodes that originally stored TiDB tenant data, TiDB1 tenant data. And TiDB server ensures that SQL processing capability remains constant. Oh, the user experience remains the same as well. DB2 has consistent data volume. On the other hand, it needs additional compute power. We address this by adding TiDB server nodes to the environment. Adding more CPU and RAM to DB2 ensures acceptable query response times. DB3 needs more storage. We can increase the number of TiKV nodes to address this. There's no need to increase the number of TiDB server nodes for DB3 because, well, we don't need to do that. As you can see, splitting compute and storage makes our lives much easier. It also reduces cost because we don't have to pay for resources that are not needed. As I mentioned previously, Forrester Research made up the term translytical to describe a new generation of data platforms that combined transactional and analytical processing capabilities within a single environment. So let's discuss multi-tenant clusters that do not possess translytical capability. That is, do not possess this ability. So traditional single and multi-tenant databases often cannot handle transactional and analytical business simultaneously. They require time-consuming ETL conversions to be implemented in two different database systems. For example, you run your transactional workload in Oracle and your analytic workload in Teradata. This approach requires multiple systems and an ETL process to move data from the transactional system into the analytics system. This is a lot of work and usually winds up being a maintenance nightmare. On the left-hand side of the diagram, we see our old friends DB1, DB2, and DB3. Although I haven't mentioned it, these databases are primarily transactional in nature. In other words, are focused on OLTP. So let's assume that the single-tenant architecture DB1 has a requirement for online analytics processing, or OLAP. We would need to set up a new system for OLAP, that is, install a new environment, and we would need to develop an ETL process to move data from the OLTP side to the OLAP side. Let's look at the right-hand side of the diagram. If we move to a multi-tenant database that doesn't include translytical capabilities, we must set up a similar environment. The main problem with this approach is that we don't have one environment that can handle both OLTP and OLAP. In the world of analytics, data stores, and databases, columnar storage is popular. Columnar databases can aggregate data rapidly because they don't have to read through all the data in a row. There are multi-tenant databases that include both row-based and column-based data on a single server. This gives the first impression that multi-tenant databases simultaneously support row-based data replicas for OLTP business and column-based data replicas for OLAP or OLAP business. The key issue is that this design does not separate OLTP workloads from OLAP workloads. OLAP workloads typically consist of SQL operations that consume a lot of I/O and long-term CPU power, such as generating reports, evaluations, or risk analysis. Storing row-based and column-based data on the same server results in unpredictable response times for our OLTP workloads. The reason for the unpredictability is the long-term CPU usage of OLAP workloads. This means that OLTP queries may not meet their response time requirements. Let's summarize by saying, storing row-based data and columnar data on the same server is not a good solution for tenants who have both OLTP and OLAP businesses. TiDB solves many of the OLTP and OLAP problems we discussed on the previous slide. TiDB is designed to store row-based data and columnar data in a single environment. As we mentioned previously, row-based data is stored in TiKV. TiDB also provides a storage engine for columnar data. This storage engine is called TiFlash. You may be asking, why does TiDB provide different engines for two storage types? Well, we do this to ensure that the columnar storage operations do not adversely affect row storage, and so that row storage does not adversely affect columnar storage. This empowers TiDB to service both online transaction processing and online analytics processing. Each and every TiDB tenant can use TiFlash storage. In addition to storing data in columnar format, TiFlash uses a massively parallel processing computation architecture that is extremely efficient for large table joins and mass data aggregation. It's important to note TiDB requires available TiKV storage. On the other hand, TiFlash storage is optional. You can choose to use it based on your use case. For example, Table 2 has both OLTP and OLAP use cases, so we use both TiKV and TiFlash engines. Fortunately, TiDB handles all the data replication between the TiKV and the TiFlash sides, so there's no ETL or ELT required. It just works. Table 1 only services an OLTP use case, therefore we only have to have TiKV storage allocated to it. Remember, each table must have TiKV storage allocated to it. When you separate compute and storage, users benefit. Users don't need to know about TiKV and TiFlash because the TiDB optimizer, which lives in the compute layer, chooses which one to use based on the SQL. Speaking of SQL, and this is really cool, assume that you have a table named foo, which only has TiKV, that is row-based storage. The DBAs decide to add TiFlash columnar support to the table foo. Your queries will be able to use both engines without you doing anything. The compute layer, TiDB server, automatically routes operations that require precise indexing to the row-based TiKV and routes operations that require full table scans and basically large scans of data to TiFlash. This was previously unimaginable for a single tenant system relying on ETL tools. These single tenant users had to know which database to use for their SQL statements. We have a great name for this, and it's called HTAP, HTAP, and that means Hybrid Transactional and Analytic Processing. So in summary, TiDB's HTAP design for multi-tenancy allows us to have both row and column store versions of data with resource isolation. We no longer need to worry about synchronizing data between disparate row and column stores. We don't even need to consider which database to execute SQL queries on because TiDB is a single environment with a single SQL interface. We get to determine on a table-by-table basis whether or not to add columnar data to a table. All of this is based on our use cases. In order to create and manage our TiDB multi-tenant database, we need tools and utilities. When you're getting started, the most pressing need is database operation. This includes installs, Kubernetes management, and backup and recovery. Fortunately, we have this covered. TiUp is a tool that helps users install, manage, and upgrade TiDB components. TiUp simplifies the installation process by providing a single command line interface to manage all components of the TiDB system. It also helps with version management, so users can easily upgrade or roll back to previous versions if necessary. TiDB Operator is a tool that helps manage and automate the deployment of TiDB clusters on Kubernetes. TiDB Operator combines the benefits of both technologies by enabling users to deploy, manage, and scale TiDB clusters on Kubernetes with ease. It automates the process of creating, updating, and deleting TiDB clusters, and also monitors the health of the cluster components. TiDB BR is a backup and recovery tool that helps to create, manage, and restore backups of TiDB databases, ensuring that users have a reliable and secure way to protect and recover their valuable data. Next, we need to monitor our environment to ensure that it is working properly. First, we have Prometheus and Grafana. They're two popular open source tools that are widely used in the monitoring and observability of software applications and systems. They provide a powerful and flexible way to monitor and visualize the performance of TiDB clusters. They allow users to quickly identify and troubleshoot issues and make data-driven decisions about their TiDB clusters. TiDB Dashboard is a web-based user interface for managing and monitoring TiDB clusters. Although similar to Prometheus and Grafana, TiDB Dashboard is a centralized management and monitoring tool for TiDB clusters, while Prometheus and Grafana are monitoring and visualization tools for more focused on collecting, storing, and visualizing metrics data. Although there's some overlap in their functionality, they serve different purposes in the TiDB ecosystem. Next up, we have Clinic. Clinic is a performance analysis and optimization tool that helps users to identify and optimize the performance of their TiDB clusters, providing a valuable tool set for managing and optimizing large or complex TiDB deployments. Finally, we have the data platform. TiDB Dumpling is a tool that helps export data from TiDB databases. It allows users to export data into various formats such as SQL files or CSV files, making it easy to backup or transfer data into other databases. TiDB Lightning, on the other hand, is a tool that helps import data into TiDB databases. It is designed to be fast and efficient and can handle large amounts of data. TiDB Lightning uses the TiKV import mechanism, which allows it to quickly load data into the TiDB cluster. That means that basically you're bypassing SQL processing when you load this data. TiCDC is a utility that captures and replicates changes in TiDB databases in real time, providing users with a powerful tool set for managing data replication in the TiDB ecosystem. TiDB Data Migration is a tool in the TiDB ecosystem that helps migrate data from third-party databases to TiDB databases. And finally, Sync Diff Inspector is a utility that helps identify differences in data between two TiDB clusters. Let's return to the purpose of database consolidation. It helps to reduce cost and improve efficiency. Previously, we discussed that the cost problems in multi-tenant databases are often caused by the different needs of each tenant. Some tenants need more storage, some tenants need more computing power. This causes problems such as increased cost for storage and compute. It's also wasteful because if a system needs more storage, you have to add compute too. This is where TiDB and its separation of compute and storage save the day. If you need compute, add compute. If you need storage, add storage. The TiDB database provides some fine-grained control functions for resources, such as resource control that can allocate computing power and storage capacity on demand without unnecessary allocation. Placement rules and SQL control differentiated high availability levels. Classifying data storage as hot or cold helps us save money as well, and differentiated scale based on storage and computing power that can expand or shrink each tenant individually. All these help us refine cost control, and only by doing so can we adjust cost allocation based on differences of each tenant. TiDB Database's resource control can automatically schedule more computing power or storage capacity for tenants whose load suddenly increases or decreases. Features such as hot and cold separation and HTAP are effective functions aimed at ensuring that the system response and user experience are not affected after integrating data from multi-tenant databases. Therefore, we can see that choosing a suitable multi-tenant database for database consolidation can be crucial in reducing cost and increasing efficiency through fine-tuned control, and this is something that we must consider. So to review what we discussed, resource control helps with cost and efficiency. Placement rules in SQL also help with cost and efficiency. Scale helps with cost, and HTAP with efficiency. We will discuss customer use cases. Our first case study covers a gaming company. The diagram shows the company's abstract architecture. We will see their specific database architecture shortly. So the diagram shows that the gaming company's high-level architecture consists of a game engine and 3 subsystems. Audience management, which manages our users' information. User reward management. This assists in keeping track of play so the system can extend rewards to users. And user tag management, which helps track users' behavior. Let's take a look at how they've arranged their databases. This gaming company was using Amazon Aurora and Amazon Redshift to store their data. We called out this situation previously. It takes multiple database systems, not just database instances, to handle OLTP and OLAP. Remember, this increases expense and makes it difficult to manage because you must learn multiple database environments. So, a little bit of background. Amazon Redshift is a cloud-based data warehouse service designed for large-scale analytics and reporting. Redshift users commonly report performance issues. Users also report issues with data management, specifically loading, unloading, and updating data. Other users have commented on the steep learning curve required to learn Redshift. Finally, while some users find Redshift cost-effective, many large users find it very expensive. Amazon Aurora is a cloud-based relational database designed for high availability and fast response times. Many users are hampered because Aurora doesn't offer the same features as other databases. This makes it difficult to migrate environments to Aurora. Aurora provides limited configuration options as well. This makes it less flexible than other databases. Finally, and this is a big one, like Redshift, Aurora is expensive if your environment houses a lot of data. We also mentioned that when you use multiple databases, you must do an ETL, which also adds expense. This system design is a great candidate for database consolidation. We know from our previous discussions that the subsystems will have varying levels of criticality and that TiDB can effectively allocate resources to meet this requirement. We've replaced Aurora and Redshift with a multi-tenant TiDB environment. The customer is pleased because throughput increased by 3 times, the system has horizontal scalability, they have experienced 0 downtime, real-time hybrid transactional analytical processing, or HTAP, has made their lives easier, operation tasks have been simplified, and they didn't have to change their application to get this new system up and running. Let's discuss a second case study. This customer had more than 100 MySQL instances. This customer was facing a situation like the one in our first case study, but on a much larger scale. The sheer number of MySQL instances makes monitoring, troubleshooting, upgrades, and security a challenge, and a challenge may be putting it mildly. Not only were there numerous MySQL instances, they had a lot of data too, 330 plus terabytes, and this includes a 3-month window of hot data that all combined reached approximately 80 terabytes. This company was a great candidate for a database consolidation project. Let's see how they handled it. They moved their 100 plus MySQL instances to TiDB. They gained the same benefits as the gaming company we previously discussed. So let's talk about these out of order. Consolidating their databases reduced operation and maintenance complexity, and it improved efficiency. These factors drive down costs too. Business isolation. They maintained their previous model of keeping their business data separated from other data. Let's return to the first bullet. Cold and hot data storage tiering reduced storage costs. Separating hot and cold data allows us to store cold data on lower cost HDD drives. And not only are HDD drives less expensive,
They provide greater storage space. Recall that cold data is not accessed often, and when it is, a lesser level of performance is acceptable. This strategy enables customers to save money by using less expensive drives. Look at the left-hand side of the diagram. You'll see the word hybrid. Business 1 and 2 are not vital to the overall business of the organization. They have low data volumes and aren't used often. This customer used a hybrid approach for these databases. They deployed them on a single TiKV node. Compare this with business 3 and 4. They were deployed using the exclusive model. Each of these databases TiKV nodes exclusively dedicated to each of them. Business 3 has TiKV node that only it uses, and Business 4 has TiKV nodes that only it uses. This results in physical isolation of databases from other businesses. Notice that the hybrid and exclusive approaches both use high-performance disks. In reality, these are SSDs. Finally, the cold data area is placed on a dedicated TiKV server, which run low-performance disks. In this case, they are HDDs. I have a question for you. Can you remember how we separated hot and cold data? If you said placement rules, you are correct. Let's take a moment and summarize what we've learned. We've covered a lot during our discussions. Let's review some of it. First up, cost and efficiency. We discussed how database consolidation can help us reduce costs and increase efficiency. TiDB's separation of compute and storage comes into play here. If we need more compute, we add compute. If we need more storage, we add storage. Next, isolation. Each database may have different performance characteristics, data volumes, and availability requirements. Our new database must be able to manage these divergent requirements. We discussed how resource control, which is another way of saying I want to put something in a specific place, is controlled by placement policies in TiDB. We covered how data has different access patterns. Some data is accessed all the time and other data is rarely accessed. We call this hot and cold data. We also discussed how TiDB can implement this type of strategy using placement rules or placement policies. This leads us to differentiated high availability. Tenants will have a varying HA requirement. We discussed how TiDB enables this as well. Next, scalability. A multi-tenant database needs the ability to scale. Individual tenants need the ability to scale too. We discussed how separating compute and storage allows TiDB to scale easily. We also discussed how placement policies empower us to control tenant scaling. Translytical capability. Translytical describes a new generation of data platforms that combine transactional and analytical processing capabilities within a single system. Combining these into a single system eliminates the need for ETL. We discussed TiDB's TiFlash component and how it adds column-based analytics to TiDB. And finally, easy to operate. Going from one database management system to a single one makes learning and managing the system easier. Going from a multitude of database instances to a single TiDB cluster makes your life easier too. We mentioned several important features of TiDB as a multi-tenant database: resource control, placement rules in SQL, and HTAB. Here we provide hands-on experiments for all of these features, so you can follow the step-by-step instructions and experience these functions in your own environment. Thank you for taking the time to complete this training. We hope that you learned a lot and enjoyed it.
If you want to learn more, scan this barcode and then you can get access to more PinCap training and certification resources.